Time to learn about Stokes Theorem. Okay, so I suppose that Stokes Theorem, in some of its forms, is kind of the most general version of the divergence theorem that we learned previously. But as it usually appears in a Calc 3 class, it's actually harder to generalize. But it's usually written as this equation here. It says that if I take the curl of a vector field and integrate over a surface ds, then I get the line integral of the vector field around the boundary. Now, both of these sides of this equation are integrals that depend on orientations, so it's important to have the orientation of the surface with its boundary chosen in a coordinated way. And usually the way this is done is it says, okay, if n is the normal pointing at you, so in other words, if you position yourself in space so that the normal from the surface is pointing at you, then the way to orient the boundary is to give it what's called positive orientation, which some people say is counterclockwise, and that'll work fine on surfaces without holes, but the best way to view it is that the surface is quote-unquote on your left, and I'll show what I mean here. In any case, but so in the simple case, and here I've made a little, here I am up in outer space looking down at this surface, and I've oriented the surface and its boundary in a way that makes sense insofar as the normal is pointing at me, okay, and boundary S, from my viewpoint here, is oriented in a counterclockwise way. So it's around the curve this way. And so with this orientation of this boundary curve, and with this orientation of the normal, this equation would hold for any nice, smooth vector field F. Okay, but more generally, and I mean, okay, so counterclockwise usually means something, you know, that's pretty obvious. Here's counterclockwise for this surface, assuming that I'm up here somewhere and that the normal is pointing at me. But the idea of the surface being quote-unquote on your left is better when your surface has holes, because the point is that it'll go, I mean, your boundary to the surface now includes this on the outside, but it also includes these curves here, and these have to go in the opposite way so that the surface is sort of on your left as you're traversing this curve. Okay, you imagine that you're walking along this curve, you want the surface to be on your left. If you're going around this way, the surface would be on your right. Okay, and similarly here, these would have a clockwise orientation in order to keep the surface, quote-unquote, on your left. Okay, so there is your divergence, your Stokes theorem in 3 dimensions, the way you're likely to see it, along with how to coordinate the orientations so that it works, okay, and so that you're not off by a negative sign. Now, I don't care about it too much, but I want to mention it at least, and here's a sort of thing where you can pause it if you're interested, and I'm going to fly through it, but if I take as my vector field something that depends only on x and y and has a 0z component, then I can quickly derive what's called Green's theorem, okay, and I unfortunately doesn't fit well here, but the basically Stokes theorem tells me that this quantity here is equal to this quantity here, and when I assume that my surface lives basically in the xy plane, okay, the z coordinate is 0, so that it's basically a set that's completely in the xy plane and just, you know, the z coordinate 0 everywhere, then I can derive this formula here, which is that this quantity is equal to this quantity, okay? And this is seen in various places and known as Green's theorem, okay? But it's a specific case, if you will, of Stokes theorem. Okay, so with any of these things, the thing to do then is to, well, kind of verify it. So I'm going to do an integral over a vector field, or the curl of a vector field. Well, I have my curl f. Well, here, f is 2z, comma 2x, comma 2y. And the curl is 2, 2, 2. Okay? It's kind of boring, but fine. And I want to consider the surface, which is the disk of radius 5 living in the xy plane so that z is 0. Okay? And, well, if I take the curl, what is the unit normal vector to this thing if I'm above the... Let me draw a picture of what's going on. Now again, I have me up here, happy, and looking down on this disk. Okay. And the disk, I'll assume it's pointing up at me. The orientation is, so it's pointing towards me. Okay. And this unit normal is just k hat. So if I take my unit normal to be k hat, which is 0, 0, 1, and I dot it with this 2, 2, 2, I just have the number 2 in here, which means I have an integral that's going to give me 2 times the size of this disk. So 2 times pi r squared, so 2 times pi times 5 squared, so 50 pi. Okay, so I just computed what you can view as the left-hand side of Stokes' theorem for this surface, which is just a disk. Okay, right? I got 50 pi. Okay, now I want to compute the other side of Stokes' theorem, where this has a counterclockwise orientation. Okay, and I'm going to imagine now I'm going to integrate on this circle. Okay, this is a circle drawn with perspective because I'm up here, and here, I'll give myself arms and legs again. Okay, so I'm looking down, it has counterclockwise orientation, and I proceed to parameterize the curve, and, well, I do the integral. And sure enough, I end up with 50 pi, which matches up with this 50 pi, and so I am happy. Okay, one more thing I'm going to do, though, before I conclude this lecture, and it'll be a fairly short lecture. And I guess, I'll mention here, you should send an email to your recitation instructor saying that you watched the Stokes Theorem lecture. That's all I'm going to require of this. It doesn't appear on the previous quiz. And frankly, it typically in this other semesters, it doesn't appear on the final exam anyway, but I always present it. Okay, but now you can make a little complaint about what I've done here and say, the surface I picked, which was this disk, lives in the plane. And this is really a theorem about surfaces that live in 3 dimensions. So therefore, let me do one more surface before ending the lecture. Let me do the hemisphere that happens to have the same boundary. Okay, so I'm now taking the the hemisphere that's open at the bottom would have this, again, this circle as its boundary. Okay, and so S2 is, I start with the sphere, and then I say, but only include z greater than or equal to 0. Okay, and so it has the same boundary circle. And so that way I already know that when I integrate over the boundary circle, assuming, again, I take the normal vector pointing at me, I already know that the integral over the boundary circle is going to be 50 pi because I did it here. Right? That was this computation here. Okay? Okay, so in terms of the fact that I have a hemisphere, well, I chose radius 5 so I could steal all of the old stuff, which is what I do. It's a hemisphere, and this screwed me up. I forgot that my v has to stop at pi over 2. Okay, u goes all the way around. R of uv, like so. The normal we computed was minus 25 sine v times this happy creature. And the normal points inward. Okay, it points in the wrong direction. It's not pointing at me, it's pointing away from me. So for that reason, I multiply by -1. Okay, because otherwise I'm basically doing it all with the wrong orientation. So to get it right, I have to multiply by -1. Okay, but well, to make a long story short, it does indeed work. I do indeed get 50 pi again. Okay, I have to take the of f dotted with big N, which is this guy. Okay, since I'm doing the whole parameterization thing. Curl of f was 222. I dot it with that happy thing. The first two terms, the u components, integrate out to 0. If I integrate cosine u from 0 to 2 pi or sine u from 0 to 2 pi, I'm going to get 0. So the only part that matters is this cosine v. And so what do I have? Well, I have a -1 times a -25. That's positive 25. There is 2 cosine v times a sine v, and there's a 2 pi from the u integral of a constant. There's my 2 pi. This 2 I put here, and okay, I do the integral, and sure enough, I get 50 pi. Which, again, makes me happy because it's matching up with the other integrals that I did. Okay, so I guess that's the last bit of required lecture. I do plan to put another lecture up, though I probably should grade even before doing that. So that other lecture, which is optional, might not go up for another week even. Anyway, sorry that the semester was messed up by all of the nastiness that is COVID. Okay, best of luck in the future.